Hello and welcome to this Chemistry World webinar. I'm Natalie Starkey, Chemistry World Science Media Producer, and I'm here with you for the next hour where we'll be hearing from three scientists from XAS who will explore the utility of Lab XAS as an everyday tool for materials characterization. I'd just like to point out that this webinar is recorded, so if you find that you've missed anything today or you just want to go back and watch again, then do look out in your inboxes for a link to the recording in the next few days. Now, here at Chemistry World, we're very happy to be working together with XAS for the first time. They're a global leader in laboratory XAS and XES instrumentation and innovation. These bulk-sensitive, element-specific techniques are powerful tools for gaining insight into oxidation state and local structure for materials characterization. Their proven laboratory X-ray spectrometers give synchrotron quality spectra and game-changing scientific freedom. Imagine what you can do with reliable everyday access to advanced X-ray spectroscopy in your own lab. Now, today I'm very happy to say that we're joined by Devin Mortensen, William Holden and Zachary Liebens-Higgins from XAS. Dr. Devin Mortensen is the CEO and co-founder of XAS. He has a PhD in physics from the University of Washington in the USA and has been working on lab-based X-ray spectroscopy for the past 10 years. Dr. William Holden is CTO and co-founder of XAS. William also has a PhD in physics from the University of Washington with a focus on laboratory X-ray spectroscopy instrumentation and theoretical modelling of sulfur and phosphorus X-ray emission. And we also have Dr. Zachary Liebens-Higgins, who has a PhD in physics from Binghamton University, USA, with a focus on lithium-ion battery materials. At XAS, his focus is on instrument and sample testing as well as R&D. Now, our speakers today have made a recording of their presentation for the webinar, which we will watch very shortly. And you'll be really pleased to hear that Devin and Zach are also joining us live on this call. So I'd like to welcome them on the screen now. There they are, you can already see them. Devin and Zach are here to answer any questions you might have on today's topic, because as with all Chemistry World webinars, this session is interactive. So if you'd like to ask a question to the team, then please use the questions box, which you'll probably find down one side of your screen in the GoToWebinar panel. And you can pop your questions in there at any point during the webinar, and we'll be able to put those to our panel of guests during the live Q&A that is at the end of the webinar after we've seen the recording. Now, you won't usually be able to see other people's questions in that box, but don't worry because your questions will be getting through to us. Myself and the Chemistry World webinars team can see all of them, so do start sending them in really soon. We also have another XAS employee working in the background, so we may be able to get back to some of you on the questions box, and other questions we'll be able to put to Zach and Devin in the Q&A. So get them all coming in. If you don't get your question answered, then we'll provide details at the end of how you can get in contact with the team. But just before we begin the presentation, we have a short poll for the audience just to gather a little bit of information about you. So we're going to get that up on screen now. And then you can interact with this poll if you'd like to. We'll give you a couple of minutes to have a look at the question. The question is, what is your level of experience with X-ray absorption spectroscopy? So you've got 5 options, maybe none of the above is the final option, but you've got previously heard of that technique. You might have mailed in samples for measurements. You might have hands-on experience of testing samples at the synchrotron. You might have hands-on experience with specialized sample environments. So it would be great for the team to know who we've got in the audience today and your experience of using this technique. So I've got currently quite a lot of people saying answer 1. They've previously heard of it, and we've got a fair proportion of the audience saying none of the above. So that's going to be really interesting for the team. I'm going to give you a couple more moments to click on your answer. Thank you to all of you. We've got, wow, really nearly 70% of the audience have voted on that, so that's great to see. There we go, thank you so much. That's going to be really helpful for the team to see. So without further ado, we're gonna launch the recording of the presentation, and then, as I said, keep sending in your questions, and I'll see you after the recording where we'll have Devin and Zach back on screen to answer all your questions. Thank you.
Thank you to the moderator for that wonderful introduction. And of course, thank you to all of you for attending today. We're really excited to talk to you about X-ray absorption spectroscopy and the unique capabilities it provides for materials characterization. Today we're going to start with an introductory overview of the technique, along with some example applications. Next, we're going to look at the recent instrumentation enabling this methodology at the laboratory scale, and then we're going to move on to a real-time demonstration of data collection. Let's begin with the question of what is X-ray absorption spectroscopy? Some of you watching this webinar may already have familiarity with XAS, but I wager many of you do not. It's certainly not as widespread as some other materials characterization techniques, and that's for reasons we'll get into a little bit later. The short answer is that X-ray absorption is a unique analytical method used to investigate and characterize materials at the atomic and molecular level. Slightly longer answer, XAS is specifically the fine structure observed in the energy-dependent absorption of a material over regions near the binding energy of a core level electron. The most straightforward method of observing this is in a sample transmission geometry, as what's shown here on this slide. The logarithmic ratio between incident and transmitted intensity will tell you the amount of absorption that's happening in your material. Recording this over a range of incident X-ray energies together generates an XAS spectrum. So let's take a look at what an actual XAS spectrum looks like. Starting here below the binding energy, absorption will tail off smoothly as high energy X-rays are more penetrative, right? So more penetration, less absorption. And this continues smoothly until you get to regions near and above the binding energy. Here, additional absorption turns on as the X-rays can be absorbed by a core electron, first transitioning to unoccupied atomic states before then becoming an unbound photoelectron once the binding energy has been exceeded. The region is commonly referred to as XANS, which stands for X-ray absorption near-edge structure. As you go to measure the higher energies above the binding edge, you have what is called the extended X-ray absorption fine structure, or XAS with an E. In both the XANS and the extended, scattering of the photoelectron by neighboring atoms gives rise to interference patterns in the absorption spectrum. The fine control that you have over the photoelectron momentum, and this is done by controlling the energy of the exciting X-ray, means that essentially what you have is you have a scanning wavelength interferometer that's centered locally around a specific atom. As I mentioned previously, XAS provides some unique advantages when it comes to materials characterization. First, because the fine structure occurs specifically at energies around the binding energy of a core electron, and different elements have different characteristic binding energies, XAS itself is an inherently element-specific probe. What this means is you can have a whole mix of elements in your material, and you can probe the chemical state of each one individually. Second, the use of hard X-rays means that it's a bulk-sensitive technique on the scale of several to tens of microns. This makes it a good complement to more surface-sensitive techniques, such as, for example, XPS. Third, the XANS, the near-edge region that we talked about, the different oxidation states have unique fingerprints. This makes it well suited for linear combination fitting to extract oxidation information on an unknown sample, or to simply track changing oxidation that's going on during a chemical reaction. Fourth, XAS only probes the local structure. And what that means is that it works well on crystalline, nanocrystalline, or amorphous samples. There's no long-range order required in order to get an XAS spectrum, such as would be the case, for example, X-ray diffraction. Lastly, since it's hard X-ray in, hard X-ray out, it's very well suited for in situ measurements, where here the absorption by just the material and the geometry of the cell can be challenging for some other techniques.
Now let's take a look at a concrete example and see how the unique advantages of XAS can be applied. So here we have a fully assembled lithium-ion pouch cell. It has a nickel manganese cobalt oxide cathode, NMC532, on a 20 micron aluminum foil backing. It has a graphite anode on a 10 micron copper foil backing. So the challenges of this sample are, we'd like to be able to investigate individually the changes of the nickel, manganese, or the cobalt to see how they participate in the cycling of the battery. We'd also like to be able to measure it non-destructively, right? We want to see how these elements are behaving in the assembled battery without having to take it apart. Lastly, we'd like to be able to extract information about the oxidation state of each element and probe how these states can vary based on the charge state of the battery. So what is the solution to these measurement challenges? This is where we can use laboratory XANEs. So here's a plot of XAF scans measured on the nickel K edge around 8.3 kiloelectron volts. So the blue trace is a reference nickel metal foil used for energy calibration. The red trace shows a measurement on the pouch cell and the fully discharged state. As you can see, the energy position of the rising edge is higher in energy compared to the nickel metal, showing that the nickel in the cathode is in a higher oxidation state. The green trace shows the same measurement on the pouch cell after it has been fully charged. So it's clear that the energy position from the edge for the green trace is shifted towards higher energy, showing that the nickel atoms in the cathode were further oxidized during charging, showing that the nickel atoms participate in the charge compensation. This experiment can be repeated for intermediate charge states as well, and it is even possible to do operando to see smooth transition in oxidation state during charge and discharge. So it turns out that the standard battery pouch cell preparation in terms of mass loadings and metal layer thicknesses is a good match for transmission mode XAFs. So in this plot, you can see very good data quality can be achieved even in just 8 minutes. You can even optimize further. For example, if you just want to get really good quality near the edge and can be a little bit noisier outside of there, you can see that the features are clearly resolved even with only a 2-minute scan. So these shorter measurement times can enable operando measurements of battery cycling even at high charge and discharge rates. Measurements on other elements in battery materials like the manganese and the cobalt, as well as operando measurements, have been performed by a number of groups on batteries and battery materials. So here's a short list of some recent published results that include measurements performed on batteries using EasyXAS instruments. So to see details of these and other publications, you can reach out to us by email or visit our website to download our full list of publications that include measurements made on EasyXAS systems.
In addition to the chemical and oxidation state sensitivity, the XAFS portion for this technique can be used as a local structure probe of the element of interest. With structural models, a wide range of information can be gained about the coordination environment and bond distances. In particular, the XAF spectra is often tracked in situ and operando setups to directly monitor the evolution of the local structure. Looking at this in practice, we see the typical oscillations for a nickel oxide reference pellet. These XAF oscillations can be described in terms of atomic distances, as shown here for the nickel oxide and nickel metal systems. In this case, the nickel oxide has 2 distinct features between 1 to 3 angstroms associated with the nickel oxygen and nickel-nickel atomic distances in the rock salt structure. The nickel metal has a single nickel-nickel peak. XAFS fits of these structures provide direct insight into the atomic distances, which can be valuable in identifying material or observing the evolution of a material structure. When we consider the chemical and structural sensitivity of the XAF technique, there are a wide variety of applications where this information can be used, particularly in materials characterization, design, and applications. This includes catalysis, environmental studies, and lanthanide actinide research. These papers are just a small subset of the applications that laboratory XAF spectrometers have been used for. For environmental and actinide research, this work can involve hazardous or radioactive materials. The use of laboratory XAF spectrometers enables new opportunities to study the materials without needing to bring them to a synchrotron facility. Now, of course, XAFS is not the only technique that provides structural, elemental, and chemical sensitivity. Diffraction, fluorescence, and photoelectron spectroscopy are all commonly used in material science laboratories. However, XAFS does offer a unique structural and chemical insights beyond these other techniques. The additional sensitivities that the XAFS technique offers include short-range order, chemical analysis, and bulk sensitivity. These sensitivities make XAFS an important part of a material scientist's toolkit.
By now, you've hopefully bought into this concept of XAF as a useful technique, and hopefully have some ideas about how it could provide value specifically in your research and work processes. The next question then is, how is it done? What equipment do you need? How do you get access? Well, for most established materials characterization techniques, the access curve typically follows this pattern shown here, where the availability or ease of acquiring equipment is inversely related to the technical capabilities required, right? So if you want to just do something really simple and easy, there's some cheap equipment you can buy for that. If you're wanting to do something that's really pushing the forefront of science, there are, hopefully large-scale facilities to be able to support that. Historically, XFS hasn't populated this whole curve and instead looks more like this. The reason for that is that since XFs first started being used as an analytical tool in the 1970s, experiments have almost exclusively been run at synchrotron light sources. There are currently several dozen of these facilities around the world, and there are, of course, many experiments run at these, not just XAFs. So what you have is you have about 200 beamlines that are dedicated for XAFs measurements. So that's 200 for the whole world. While these light sources provide incredible utility for cutting-edge science, they're also a considerably limited resource. As you can imagine, this has led to very high competition, massive oversubscription, and limited access even for what would be considered a successful user, right? If you're a successful synchrotron user, you're getting access maybe twice a year. It has always been our belief that the lack of smaller scale instrumentation has really handcuffed XF's potential as a more routine analytical technique. This delay potential in turn means that there has been a lot of missed opportunities in both research and industrial applications. So in 2015, we've established EasyXFs in order to specifically address this problem. Our mission is to elevate XFs from a niche technique used only by a very select few to a more standard analytical tool that can be used by everyone doing materials characterization. And as I said, the way we do that is with lab scale equipment.
So how does this actually work in practice? So here's a view inside of our flagship instrument, the EasyXF 300+. The main components of the system are an X-ray tube to generate broadband X-rays, a crystal analyzer to select out a narrow range of energies, and a detector to measure the X-ray flux through the sample. For the X-ray tube, we use a 1200 watt XRD-style liquid-cooled X-ray tube. We use either a silver or a molybdenum anode, depending on the measurement. In our case, we aren't using the characteristic lines from the anode. We're using the smooth broadband output from the Bremsstrahlung portion of the X-ray tube spectrum. As this style of tube is commonly used in XRD systems, the technology is reliable, proven, and low maintenance. The next key component is the spherically bent crystal analyzer. This is at the heart of every EasyXF's instrument. So similar to a prism for optical light, using Bragg diffraction, the crystal analyzer selects out a nearly monochromatic energy from the broadband output of the X-ray tube. So the crystals can either be silicon or germanium, and by using different orientations for the crystal wafers, we can measure different energy ranges. For the detector, we use a silicon drift diode. So the advantage of using this detector is that it measures the energy of every single X-ray detected to within a couple hundred electron volts. So that allows us to pick out the monochromatic beam from the crystal that we want to use for our measurement and separate that from potential backgrounds that we don't want or unwanted harmonics. Okay, so now I have the opportunity to show off a fun 3D animation that I made to illustrate this. So we have the X-ray tube, crystal analyzer, and the detector. So from the output of the X-ray tube, we have polychromatic X-rays going towards the crystal analyzer. And then a single X-ray energy, indicated by a single color, is coming back to the detector. So as we change the angle between these components, the energy being refocused onto the detector changes as well, as indicated by the changing colors. So this is how we achieve a monochromatic, tunable X-ray beam that we can sweep over a range of energies to build up our XF's measurements. Letting that animation play through one more time, we can see how the components move relative to one another. So there are 4 motors that control the positions of the components to achieve the desired changes in Bragg angle to step through the energies of the measurement. So bringing that back into the context of the instrument, so here we have a picture with the components illustrated. So at a single position, the broadband 0 to 40 keV X-rays are generated by the X-ray tube, and then they're diffracted by the crystal analyzer and come back to the detector with a narrow bandwidth. So here schematically, 8,000 plus or minus around half an EV. So as shown in the animation, we change the angle between the X-ray tube and the detector, so the diffracted energy changes, and then we go step by step, single acquisitions at each step to build the X-ray absorption spectrum. The energy range of the instrument is from around 4.5 keV up to around 25 keV. So as you can see on this periodic table, that covers well the energy range of the K edge for 3D transition metals, as well as the L edges for the lanthanides and for the 5D metals. So as you go to higher energy, there isn't a sharp cutoff, but the X-ray flux is reduced. And that's from lower generation from the X-ray tube and also reduced efficiency of the Bragg diffraction from the crystal analyzer. So like the example I showed earlier, a nickel K-edge measurement could be measured as quickly as just a couple minutes, while if you want to measure the palladium K-edge, the measurement would require several hours. In terms of how the samples are prepared, the most common method for solid samples is to grind a powder and mix with a binder to press into a pellet. So the pellets are typically sealed with Kapton tape and then mounted up in the instrument. So in this picture, you can see how we have a sample wheel with different positions that you can mount different samples in. And the sample pellets can be taped up or held on with these magnetic holders. So like the example before, it's also possible to measure a fully assembled pouch cell or other material that has like a uniform thickness. So for example, you could take directly a coated electrode film, seal that in Kapton, and measure it. It's also possible to have special environments for the sample, such as this cold stage that we customized for our system that can cool samples down to around 40 Kelvin during measurement. So this is commonly done at synchrotron beamlines, and it increases the amplitude of the extended XAS signal. Other types of samples can also be measured. So for example, here we have a liquid and a thin-walled 1 millimeter capillary. And depending on the sample composition and measurement mode, you can also use other preparations. With that background information on the instrument, now I can share some fancy footage of the systems that we had recorded with a local small production team when we did a promotional video for a virtual conference during COVID. Other than looking cool, the video adds a little context to build a better mental picture of the systems. And so you can see some people interacting with them to give you a better sense of scale for the size of these machines. Okay, let's have a look.
All of our hard X-ray systems utilize spherically curved crystal analyzers. These come pre-aligned and mounted to their own individual cartridge plates. Swapping between crystals is a simple matter, so in a matter of minutes you can be switching between different elements and energy ranges.
Using a point-to-point focus geometry, the system steps through different angles to record the energies of the spectrum.
A large area SDD detector allows for isolation of the harmonic of interest in order to boost the signal to background ratio. For best possible flux and resolution in XAS mode, we have our 1200 watt XRD style tube. This is used in our 300 level spectrometers. Commercial XRF style tubes are used for X-ray emission measurements. These tubes allow for minimum distance between your sample and beam spot, providing maximum flux for XES. A helium flight path is employed to reduce air absorption and improve flux at lower energies. Our automated XAF sample exchanger allows for programmable studies, so you can set up a series of scans to run unattended. Let the data collect while you're away.
Okay, so hopefully that video helped you get a little bit better understanding of what these systems look like. With all that in mind, now we can open the software and run through a real-time measurement demonstration. After we go through the setup of the scans, we'll let the data continue to collect in the background as we go through some more application examples. For the demonstration, we'll be measuring at the nickel K-edge. So we'll measure 3 samples of reference nickel metal foil, an NMC 442 electrode sealed in Kapton, and a pellet made from nickel oxide mixed with binder. So we'll measure 1.5 minutes per sample, and then do the same thing through an empty sample wheel spot for the I0, and then we'll go through those results together. Okay, so here we are in the control software for the instrument. So this software handles the hardware control for the motors, X-rays, detector, and we use it to set up the scans and data acquisition. It's a user-friendly graphical interface that's easy to learn, so new users can get up and running quickly. We won't go through all of the software details today, but we will run through the setup and show how we've configured the scans to run for the demonstration. The motor controls for controlling the position of the components are at the top left. So at first power on, the motors take a couple minutes to calibrate. Here the calibration has been completed already. Control of the X-ray tube is at the bottom left. So here we can change the X-ray power setting and open and close the shutter. So again, when you first power up, you have to warm up the X-ray tube, but for the demo, we already have the X-rays warmed up to 40 kilovolts and 20 milliamps. Now we'll continue to the configuration and setup in the middle. So first we'll set the save directory. Next we'll select the crystal analyzer that we're using for the measurement. So here we're using the silicon 551 crystal analyzer to measure the nickel K edge. So the analyzer radius parameter is optimized for this particular crystal and is preset to 495 millimeters. The theta offset is a calibration parameter for alignment of the beam. So this is determined by a 1-minute alignment scan. And for the demo, we've already done that, and so that's the value we have here. So next we can initialize the connection to the detector. Since I already have the shutter open and the beam is on the detector, I can hit Collect MCA Spectrum, and the detector acquires a 1-second spectrum. You can see this spectrum at the top right. Since we're using an SDD detector, we're measuring the number of X-rays and the energy of each X-ray acquired. So we have an energy spectrum of all of the X-rays measured. So that's at the top right. And so you can see the energy scale goes from 0 to 40 keV. So for the silicon 551 analyzer, there's a single intense peak from the monochromatic beam, and that's at around 8.5 keV. So these are the X-rays that we're interested in. That's what we want to use for our measurement. So we set a region of interest around that peak. The plot below that shows the zoomed in view of that ROI. So the sum total of that peak is the ROI counts. Here that's about 204,000. So that's the number of X-rays that we want to measure, and we measure that at each step in the scan to build up our XF spectrum. I'll set the measurement mode to XFs, select nickel as the element, and then we can move on to setting up a scan definition to do a Zane's check on the nickel foil. So for the scan definition, I'll give the sample a name. So here we're going to do a quick nickel foil check. Using the preset scans, I'll select the nickel K and the Zane's check mode. So here you can see this is a single constant step zone. So we'll scan the energy of the beam between these two energies, just with a coarse step size and a very short duration. So you can see this gives us a time per scan of just 20 seconds. So this just gives us a chance to see that the sample is in the position that we expect and that we're properly capturing the absorption edge that we want to see. Now I'm ready to go ahead and hit start, and the data starts collecting. So I'll just fix the auto scale on the plot, and now we can see the counts coming in. So we start around 260,000 counts per second, and you can see there's a sharp dip in the X-rays being measured by the detector as we increase the energy past the absorption edge of the nickel foil. And that's just what we expected to see. So now I could go back to the scan definition tab, and if I change the preset scan type to Zane's, you can see that gives us 3 scan zones. So we would have coarser steps in the pre-edge region, finer steps around the edge with a longer measurement time, and then coarse steps after the region. So the default is around 15 minutes, but we've got some good samples here and we've got the system optimized, so we're going to be able to do the demonstration measurements with just 1.5 minutes per sample. So now that we're ready to set up the demonstration measurements, we can switch over to the action scripting tab. So this is the system that we have for doing a sequence of actions. So for example, we can load a scan definition, we can change the X-ray power settings depending on the sample, we can change the sample wheel position, and then we can run a number of scans. So here we have it set up. So first we'll do an I0 scan. So that's where we measure through a sample position that doesn't have a sample. So we can see what the raw amount of X-rays are coming from the monochromator without any sample. So we'll do that with an X-ray power of 40 kilovolts and 15 milliamps. Then we'll increase the power to 40 kilovolts and 20 milliamps change the sample position to measure the nickel foil and do a single scan. Then we'll switch to full power, 40 kilovolts, 30 milliamps, and do one scan on the NMC 442 material, and then another scan on the nickel oxide pellet. Now that that's ready to go, I can hit start and let the acquisition start collecting. So now the motors are moving into position to start the scan. We're starting off on the I0 sample, so that's an empty sample position so that we can measure the amount of X-rays present without the sample. As the data continues to come in, we can see it's reached the portion of the scan near the absorption edge where the step size reduces to capture more detail. For the I0 sample, we are measuring with the X-ray beam power at 40 kilovolts and 15 milliamps, so that's half power. This beam power is chosen so that the detector maintains a low dead time to avoid saturation. So in the middle, you can see beneath the main plot, there's a plot of the dead time. So it's around 31%, and the target dead time is around 30%. On the I0 position, without any sample to absorb the X-rays, we reduce the beam power to avoid saturation. So before the measurement switches to measuring the samples, that's why it's set to increase the beam power, to increase the count rate. Okay, so with that, we'll let the data continue to collect. I'll move this plot off to the side and let that data continue to stream in as we go through a few more XAS application examples.
So as the demo is running, we would like to spend some more time going through additional use cases for the EasyXF spectrometers. As noted in an earlier slide, the EasyXF spectrometers provide direct sensitivity to over 60 different elements that fall within the 4.5 to 25 keV energy range. For this slide, we are showing specific examples of the low and high energy range of our systems. At the lower end of the energy range, we have a titanium reference metal versus TiO2, where we see a shift related to oxidation state. Additional features of the TiO2 line shape indicate that this sample has the rutile structure. For the niobium K-edge at 19 keV, we're able to differentiate niobium metal and niobium 4+ and 5+ oxides. These two examples highlight the sensitivity of the XF technique across elements. Beyond the general demonstration of this technique, we'd like to highlight specific examples where our customers have used this for their own applications. At the University of Warwick, Professor Lewis Piper's group have been using the EasyXF spectrometer to test commercially relevant battery pouch cells during extended cycling. In comparison to conventional coin cell testing, the pouch cell setups offer improved reliability to understand battery operation. In this case, they looked at the extended charge-discharge process of a commercially available battery cathode. XAFs was used to directly track the lithiation based on nickel reduction and oxidation. From this work, their group was able to gain new insights into the origin of lost performance during long-term cycling. As a second example, we would like to highlight how XAFs can be used to further understand next-generation lithium-ion batteries. Current battery technologies rely on liquid electrolytes for devices and electric vehicles. Solid electrolyte batteries are promising alternatives as they are expected to have improved safety and higher energy density, which would make electric vehicles safer and have a longer driving range. However, there remains overall challenges in their development, the identification and synthesis of a suitable solid electrolyte. There are a number of solid electrolyte candidates available, with research focusing on optimizing these materials for battery performance. In this recent work, Dr. Yang Hu supported the characterization of a zirconium-based solid electrolyte that was found to have increased long-term stability. In this case, XAFs was a helpful tool in the material synthesis process to identify changes in the zirconium environment with fluorine doping. So far today, we have provided highlights for transmission mode XAFs measurements. While in some cases, sub-weight percent measurements are possible, typical sample concentrations are in the order of 1 to 5% for transmission mode to achieve reliable data. However, it is well known that fluorescence mode is a suitable technique for achieving sensitivity to lower concentrations by directly collecting the elemental fluorescence from the sample at the synchrotron. When we bring this technique into EasyXF spectrometers, we found that we could measure and achieve sensitivity all the way to sub 0.1 weight percent for 3D transitional compounds, and even lower for certain elements. As an example of this fluorescence mode performance, we have Zane's measurements on a few 100 nanometer thin film of nickel oxide versus a nickel oxide pellet that we measured in transmission mode. There's very good agreement between these two measurement modes. In transmission mode, this nickel oxide thin film sample would normally be impossible because the substrate strongly attenuates the beam and we'd get no signal through the sample. However, in fluorescence mode, we are able to achieve reasonable performance on the order of a few hours. With these new fluorescence mode capabilities, this opens up the door to all kinds of new sample types and systems: thin films, artifacts, geological samples, and more. In both transmission and fluorescence mode, the overall determination of the absorption spectra requires knowledge about the incident flux and the corresponding sample transmission or fluorescence intensity. In transmission mode, the incident flux is measured through an empty sample holder. We then collect the transmission intensity through whatever sample or setup we would like to study. Here we have an example of the I0 and IT data for the copper K edge of a copper reference foil. In contrast to the small changes in the I0 data, the IT measurement has a large drop in intensity resulting from the copper K edge absorption. We can then calculate the absorption spectra from the I0 and IT measurements using the natural log equation shown here. The resulting copper K edge absorption data for the laboratory instrument is compared to synchrotron measurements. The laboratory measurements achieve good synchrotron quality energy resolution. Now, as we have been going through these case studies, you have seen the real-time acquisition of rapid XANES measurements on the EasyXS spectrometer. Here we can now see the transmission data for each of the 3 samples along with the corresponding beam intensity that has been collected as part of the demo measurement. With limited processing, we can convert the transmission results into corresponding absorption spectra. In the absorption spectra, there's a clear shift between the nickel reference 0 and the 2+ nickel oxide and NMC442 samples. In addition, there are slight differences between the NMC442 nickel oxide materials associated with differences in structure. This short measurement highlights the capabilities of XANES to give us direct insight into the oxidation state, even within a few minutes of measurement. And with that, we would like to thank you for your time and attention. We hope that we've given you new insights into how laboratory X-ray absorption spectroscopy can be a powerful tool in materials characterization, from structural to chemical insights. Please let us know if you have any questions.
Excellent. Right. Well, thank you so much for that, Zach and Devon. I'll get you both back on screen. There you are. That was such a brilliant overview. Thank you. So much detail in there, which is fantastic, because I know that the kind of people we've got in the audience are going to love that level of detail of seeing the instrument, seeing inside it, seeing what it's made up of, and then actually also seeing the software that you're using to gather those measurements. So I think that's been brilliant. We've had loads of questions coming in, as you've seen. I know you've been looking at some of those already, so I'm going to try and get through as many as I can in the time we've got left in the webinar. But just to the audience, keep sending those questions in. If we don't get time to answer your questions, then you'll be able to email or EasyXS will actually get back in contact with you. So don't worry, we'll do our best though. And if it was a really specific question, probably they'll just email to answer that, because that'll be a lot easier if it doesn't apply to a lot of people. So let's see. I'm going to get started. I've tried to kind of put the questions into a sort of order, but we may go a bit all over the place. So I'll begin with the types of samples you can measure. That's been quite a common style of question. If you can just kind of do an overview of the types of samples.
Yeah, absolutely. So, I mean, I would say most commonly we do just powder materials. So there, what you would do is, there's a few different preparation methods. Most commonly pressed it into a pellet. You can do solid samples as well. I mean, so the demo we ran actually on a battery electrode. So the key thing for X-ray absorption spectroscopy, if you're running in transmission mode, there are some restraints on sort of how thick you want the sample to be. So battery electrodes work great. There's the right thickness. We've done liquid samples. We've done samples in capillaries. There's a very wide range. I mean, the main thing is sort of just being able to tailor it to getting the correct thickness so that you can get a good signal through your sample.
Okay, thank you. That's been really good, and it does seem very versatile, which is very, very useful. So the next question, which is a great question from Rosalind, would it be possible to run air-sensitive samples?
Yes. So I guess typically, like, the simple solution for air-sensitive samples, particularly if they're not too air-sensitive, is like a Kapton sealing, where you have like Kapton tape to try and seal the sample. And that typically works for at least a few hours, depending on how sensitive the sample is. If you need even better sealing, you can use specialized like cells or sealed cells that you could seal in a glove box, for example. And that works for pellets or liquid samples. And that's easily put into the instrument and works for a variety of elements.
Okay, that's good to know. Right, so then, yeah, I think a great question related, you probably covered this a little bit already, but maybe a bit more detail on how you typically prepare samples for measurements. Obviously, we've understood you can be solid or powdered or all these different options. Yeah, but what does the actual preparation look like and how's that work?
Yeah, absolutely. So yeah, so like I said, powders are pretty common. So like the method you would use for powder is first you want to determine how much of the material you need. And we have tools built into the software that will help you do that. Usually on the scale of a few milligrams. But you calculate the amount of material you need. You want to make sure that you have a uniform sample. So right, you don't want to have isolated particles. So you want to grind it up. We'll usually add to that a binder material just to give it more to hold together. And that gets put into a die cast and pressed into a pellet. So that's for powders. One thing I did forget to mention in my first answer. So I've been talking about transmission mode detection. That's what we went through in the presentation today. There is also an alternate detection mode. That's fluorescence mode for those of you who are more familiar with the technique. But that mode has less requirements on the sample. So as far as thickness and whatnot, so you have the capability to do, for example, thin films, where that would not be suitable for transmission mode, but you can do in fluorescence mode detection.
Okay, that's good. We've had actually, I think I'm just seeing a question from Joyce, and I think you just answered it. It was how small should the powder samples be? I think you mentioned a couple of milligrams. Was that correct? I think that's probably what they mean by that.
Yeah, that's how much of the material. As far as as far as the actual area that you're probing. So we're very narrow in one direction. We're at 50 microns, and then tall in the vertical direction, about a centimeter. You can aperture that down if you'd like to sample, if you have a smaller sample, or you would just like to look at a smaller area of your sample. That can be done just by placing sort of an upstream aperture. Okay.
Right. The next question I'll move on to is really useful, actually. What are the concentration limits of the system? It's probably a bigger question than it sounds, though.
Yeah. So there's a lot that goes into this. Of course, it depends on what your element is, what your matrix that your element is in. But in general, for transmission mode, it's typically on the order of weight %, particularly for those 3D transition metal systems. And then as you switch to fluorescence mode, you can particularly push the limits of the system and go on the order of a sub-weight %. For example, for thin film samples, we've tested down to 50 nanometers, and that's relatively dilute samples. And then also in carbon matrices, often done on the order of 1,000 ppm or less.
Okay, thank you. That's been good. Right, actually back to kind of sample preparation type questions. We've had a question about how is the sample prepared for XANES measurement? That's how it's said, isn't it? XANES, I think. Or is there some other way to say that?
This is where when you get into the community, there's the split again across the pond. I would say where the Americans say XANES. I think the Europeans tend to say XANES.
Okay.
So yeah, no worries there. But no, the sample preparation is the same, whether you're doing just the near edge or if you're doing the full extended.
Okay, brilliant. A question that came in actually on email ahead of the webinar, which is brilliant, from Sanjeev. What are the major differences between XPS and XAS?
Yeah, so for XPS, so it's a photoelectron spectroscopy. So in that case, it's X-ray in, electron out. So usually more surface sensitive. You all are also getting oxidation state in both XPS and XAS, but XAS is in that case going to be more bulk sensitive, typically on the order of a micron scale. So they have kind of advantages and disadvantages, where XAS has a clear advantage in terms of the bulk sensitivity.
Okay, no, that's perfect. Right, let's move on to, yeah, we saw those demo measurements and we saw they were quite fast, as someone's noted. So how long do measurements of other samples or other energy ranges take? Like, what's the longest we could be looking at for getting some information?
Yeah, absolutely. And I mean, this gets into, again, a little bit of, it's always, you know, you got to look at the specifics of the sample and the type of measurement you're trying to do. But yeah, I mean, we've done measurements as fast as, you know, just a minute or two. We've had customers that have run, so we showed the energy range, right? So you can extend to higher energies. The efficiency starts to drop down, but you can't do it. That just means you have less flux. So I think we've seen some customers that have run for like as much as 16 hours on a sample. And that's what they needed to be able to get their statistics. So I would say, yeah. So the range can span just a couple of minutes to several hours, and it all depends on what it is you're measuring, what's the concentration, what's the background matrix, all of that. But that's a thing where if you have specific samples, feel free to reach out to us, because that's something that we can very easily run the numbers on and get a sense of what the signal will look like.
Okay, now that's good to know. Yeah, definitely. Yeah, put your information in the questions box, and that will all get over to EasyXAS after the webinar. So that's really good to know. Okay, maybe a simple question, but also quite a big one. What elements are covered by the instrument?
Yeah, so I guess don't want to go into every single one, but in general, so we can cover like the 3D transition metals, and that's what a lot of our customers are testing. So you know, nickel, cobalt, manganese for battery science, copper for catalysis, and various other elements. We can also do some of the 4Ds, a lot of the 5Ds, and then also lanthanides and actinides. So it covers a wide range of the periodic table. The main range where it doesn't cover is the very low elements such as carbon, silicon, or lower.
Okay, so yeah, we did have actually a follow-up question on that. Is will it show peaks for carbon as well as copper metal? So is that going to be a no for that then?
Yeah, so unfortunately it won't directly show the carbon peaks. If you were to see, like, I don't know, looking at like an iron, how the iron is bonded to carbon, it would give some insight into that, but it wouldn't be a direct measurement of the carbon environment.
Okay, absolutely. Okay. A brilliant question from Carlos. Is it possible to quantify elements in different oxidation states with this technique?
Yes, it is. It is possible to do that. Yeah, there've been some nice studies. For example, using so this one was using X-ray emission spectroscopy, which we didn't go into in the presentation, but it's complementary and similar in a lot of the ways to X-ray absorption spectroscopy. It can also be done with the instruments. But looking at quantification of hexavalent versus trivalent chromium, for example, in plastics. So that's a thing where it's like you would use, I mean, to do elemental quantification, you would use some other techniques such as XRF or XPS. But this is really good at doing chemical speciation. So yeah, being able to tell you, you know, of the element that's there, what is the particular mixture of the different chemical states of that element.
Okay, now that is really useful, isn't it? And definitely something that's different to those other techniques. Okay, what are the types of samples that can be used in fluorescence mode? I don't think we've answered this one, have we? We may have.
Maybe a little bit. I think we did.
Bit, yeah.
I think so. There's a lot of similarities between transmission mode and fluorescence mode and what you could test. Fluorescence mode pushes the concentration limits so that you can measure even lower. And then it also opens the door to samples that typically wouldn't work in transmission mode because they're either too thin or too thick. So this includes thin films, and then we've also tested like rock samples or more heterogeneous samples that you typically could not do in transmission mode. So it kind of opens the door to a variety of new sample environments to really understand chemical speciation and get that elemental sensitivity.
And I'll just point out, because I don't think we've caveated this yet, that fluorescence mode, so the trade-off from going to transmission to fluorescence mode is that in fluorescence mode, it does take a little bit longer to acquire data on your sample. So that's why, so yeah, for fastest measurements, if you can do it in transmission mode, that's the best. But fluorescence mode taking longer does open the door to a wider variety of samples.
Yeah, okay, thank you. Right, how does your spectra quality compare to synchrotron spectra? That is a really good question. Actually, I've been wondering that.
Yeah, that's a great question. Yeah, so we're able to recover synchrotron level resolution. So that's all determined by the crystal analyzer itself. So what the analyzer that we're using, the spherically bent crystal, I'll try not to get too into the details, but this is the same type of optic that is used in different spectrometers at the synchrotron as well. Like if you were doing RIX or HRFD or something. So it's a synchrotron quality optic. So that's what we're using in the laboratory instrumentation. And with that, we're able to get out the same energy resolution.
Okay, that's brilliant. Okay, I'm just going to say to people watching, we can see all your questions. We do just have a lot of them, so I'm really sorry if we don't get around to answering your question. As I said, EasyXS will be able to get back to you in the next few weeks, so please hold tight. We've still got a few minutes left, so I'm going to get through a few more questions. So we've had this question from Bruno. In synchrotron-based XAS, it is common to have a reference after the sample. So in each scan, we have a reference channel. How are performed the alignment of the between scans and the calibration for further analysis? So I guess they're asking about kind of how they're calibrating between runs.
Yeah. So for our instrument as well, we do you would have to do a calibration. It usually is done, before a whole set of measurement starts or at the end, and it's usually a very short process in order to reference to a metal sample. We have very high stability, so that metal reference can be used for all subsequent measurements on like the same element. And then when you switch elements, you would do like a new calibration. So rather than at a synchrotron where you're doing a calibration with every single sample, you're basically doing this one calibration, and then that will hold for all subsequent samples.
Right, so that's done at the start of a run, and then you only do that once then?
Yeah, basically when you're switching crystals or when you're switching elements, you'll do it once at the start of that element set.
Okay, brilliant. That's answered a few more questions in the box. I'm just looking through my questions box. There's so much coming in, which is brilliant. Lots of people are obviously very interested in this technique, which I'm sure is really music to your ears. Okay, so I think we've sort of answered this one. What are the advantages and disadvantages of measurements on a laboratory instrument versus measurements at the synchrotron? Obviously, as you said, it's very hard to get time on a synchrotron, so that's probably the biggest thing. But are there any other kind of advantages and disadvantages?
No, absolutely. Yeah, I mean, so we want to be clear that the laboratory scale instruments is never going to be able to do 100% of what the synchrotron can do, right? So, I mean, for things where you need the very high flux, where you need high time resolution, where you need micro focusing, the synchrotron is the only place you can go for that. The idea behind the lab instruments, so where this all started, was actually, as an academic project. So I myself, when I was in grad school, we were always going to the synchrotron to do measurements, and we just couldn't get enough access, pretty much. There was always more stuff that we wanted to measure, and that's where we started to play around with the lab instrument. So really, for me, in my experience, it's having that more on-demand access to be able to measure every day. There's also interesting things you can do with like sort of long baseline studies, for example, battery degradation over many hundreds of cycles, where you can actually do that on one sample and be able to cycle. That you can't do that at the synchrotron where you're only there for a few days. But yeah, so I mean, in our mind, it's both working together, both the lab instrumentation and the synchrotron.
That's good to know, thank you. We've had another question from Joyce, actually. In the presentation, you said it would take about 16 hours for lead XAFs, and I realized that you also highlighted different shades on the periodic table. Is there a reason why the first transition metals have deeper shading than others? Is it related to the acquisition time?
So yes, so basically the first row transition metals, those are in an optimal energy range. So those are where our instrument has the highest flux. And will be the quickest to measure. As you get to the 4D transition metals, particularly later in the 4D row, as you get to like ruthenium, and palladium. Those are at pretty high energies. Those are at like 20 to 25 keV, and our flux is a bit lower at those energies. So those measurements will typically take a longer, on the order of like a 10-hour measurement, because we're at such a high energy versus like the 3D transition metals. Yeah.
Okay, thank you. I think that's answered that perfectly. Yeah, a question from Rosalind. We've already had a question from Rosalind. Brilliant, lots of good questions. What is the lifetime of the instrument components? What would need to be replaced first, and roughly after how long? That's quite a good one.
No, that's a great question. Yeah, so the main thing is the X-ray tube source itself. So we're using the same sources that you would use in an X-ray diffractometer or in an XRF system. So that's the main thing, that it has a lifetime. There are a lot of factors that get into that, but usually, what you say, about 2 to 5 years is how long an X-ray tube will last. But those are replaceable.
Yeah.
Otherwise, as long as you're properly maintaining the system, these things should run for 10+ years.
Okay. Excellent. Right, we've got a couple more minutes left. Really good question about actually how do you process and analyze the data after it's collected? You've obviously got your software system. Yeah, what happens after that once you've got collected all your element information?
Yeah, so we have this basically a basic data processor, and that allows you to easily view the software and then convert the raw data into absorption and energy, calibrate it. And then once you have that data, it's in an easy to use format that you can bring it into traditional software that's been around for a while, such as Athena or Larch. That's more commonly used for synchrotron data analysis. So it's basically, we don't want you to relearn software. We want to use software that's been around for a while that people are more familiar with.
Yeah, that's great. I mean, I remember during my research years, every instrument you go on has a different setup and a different software, and we get the data out in a different format. Actually, I remember I used to get it, I'm that old that I used to get it printed out from some of the instruments. I had to type it all in. So yeah, no, that sounds really good, that there's, that it makes that part simple, because, you just want to get your data and actually be able to do something with it. So I think we're going to have to stop there, because we are, rapidly running out of time. We're nearly on the hour now. As I said, you're going to get replies to your questions. So just give Easy Access and these guys a few days, few weeks maybe. They've got a lot of questions to get through, but they will get back to you. You can, of course, contact them in the meantime with their email address, which I think my team has put into the chat for you. So yeah, hold tight, and you'll get some information back. But thank you. Thanks to our wonderful guests, Evan and William, who's not here right now, but who joined us for the presentation, and Zach for joining us from Easy XAS. If you missed anything, you're getting that recording, so do hold tight for a couple of days. But thank you to everyone watching for getting involved in the conversation. There's been so many questions, and we've had some brilliant feedback to our speakers, so that's really lovely to see. I'm glad you've all really enjoyed the presentation and got a lot out of it. If you've enjoyed this webinar, then please do check out chemistryworld.com/webinars for our future events. And while you're there, you might want to register for a Chemistry World account, where you can sign up to our very popular reaction newsletter that includes a weekly digest of big stories from across the world of chemistry. But from everyone here at Chemistry World, we look forward to seeing you in a future Chemistry World webinar. Thank you.